All right, today we're going to be continuing with our section on binomial coefficients. So in this section, it's called binomial coefficients, but we haven't actually discussed what a binomial coefficient is yet. So the answer to that is it's the coefficients in the expanded version of a polynomial that looks like this, x plus y to the n, where n is a natural number. So the case where n is equal to 0 is not really interesting, but when n equals 1, we would replace that with x plus y to the first, which is of course equal to x plus y. And remember, even though it's not written here, there's really a 1 in front of the x and a 1 in front of the y, and those coefficients, those numbers hanging out in front of the variables, are exactly the binomial coefficients. So for n equals 1, we have 1 and 1. When n is equal to 2, again, there's a 1 in front of this x squared, and a 1 in front of this y squared, so these coefficients are 1, 2, and 1. When n is equal to 3, we have a 1 in front of the x cubed, a 3, and then a 1 in front of the y cubed. Okay, so that's kind of the idea of what we're looking at right now. So just remember that when we're doing the polynomial expansion, so x plus y to the third means that we multiply it by itself 3 times. So when you're doing this, what you're essentially doing is taking these first two terms and foiling them, and then multiplying it by the x plus y, which again needs distribution. So the point of this class is not to be able to multiply those, although you should take a moment and make sure that you're kind of agreeing with the answers that we got so you can really understand what we're talking about in this section. But here I did want to point out that typically the way that we write these expanded polynomials is starting with the highest power of x and decreasing. So what I mean by that is we're starting with x cubed, and then we have x squared, x, and then this is actually, there's no x terms over here, right? This is like x to the 0 power. And at the same time that the power of x, the exponent of x is decreasing, the exponent of y is increasing. So we start with the term that has no y's in it, and then we have y to the first, y squared, and y cubed. Okay, so that's kind of the standard way to write it, I guess. So for an example, we can look at x plus y to the fifth. So remember, that just means, there we go, x plus y times x plus y times x plus y 5 times, right? And now I'm not going to bother multiplying this all out because, again, that's not really the point of this section. But if you would like to, you can pause the video now to go ahead and multiply that out and make sure you get the same thing. But kind of basing it on the pattern of the decreasing exponents of x and increasing exponents of y that we just talked about, we know that this is going to start with an x to the 5th term, and we know that because the n value is 5 up here, right? So we know that there's going to be 5 x's. All right, and then we're going to decrease the x by 1, so that's going to become x to the 4th, and then we're going to add in the y, so that's right, y to the 1st power. We usually don't write that exponent of 1 in there. And I'm going to leave a blank in here because there is going to be a binomial coefficient there. We just have to figure out what that is. All right, so continuing our pattern, the next would be x to the 3rd. So we decrease the power of x by 1, increase the power of y by 1. All right, do that again. That gives us x squared y cubed. Decreasing the power of x would be x to the 1st, and then y to the 4th, and then plus y to the 5th. All right, so I'm not leaving any blanks here in front of the x to the 5th and the y to the 5th because those are both going to be 1s, and we can see that kind of basing on the pattern that we observed up here. We can also think about it as the coefficients. So for instance, for x to the 5th, the only way that we're going to get x to the 5th is if we look at these 5 terms up here. Well, we need to choose each one of those terms to contribute either an x or a y. But in order to get x to the 5th power, we need all 5 of them to contribute an x. So this one has to give us an x, this has to give x, this x, and this one. And there's only one way that we can do that. So that basically means that the coefficient here is going to be a 1. And again, we usually don't write it. For the same reasons, the coefficient of y to the 5th is also going to be 1. And again, we don't write that. So we have to think about what these coefficients that I've left blank in front of the middle terms are. So again, we can think about this as, so x to the 4th times y. We need to choose 4 of these terms here to contribute an x, and that means by default, one of them is going to contribute a y. It's a little bit easier to think about how many ways can we choose one of these 5 terms to give its y to us, to get this part of our polynomial here. And the answer is there's exactly 5 ways, right? There, maybe I'll write that in a different color. There are 5 ways to choose one of these 5 terms to contribute a y. Likewise, kind of thinking about it from the opposite side, when we look at the x times y to the 4th, we need, again, of these 5 terms, we need exactly one of them to give us an x, and the rest will give us a y. And since there's 5 terms to choose from, there are 5 ways to choose which term gives us an x. All right, I'll go ahead and spoil it for you that there's a 10 here and a 10 here. All right, so there's 10 ways that we can choose 3 terms to give us an x, and there's 10 ways that we can choose 2 terms to give us an x. So the coefficients here are the binomial coefficients. There we go. Are 1, 5, 10, 10, 5, and 1. And if those numbers look familiar, they should. That was exactly the number of subsets of each cardinality that we talked about in the last section. So in the last section we said if you had a set with cardinality 5, so I don't know, I'll call it A, I guess. So if the cardinality of A is equal to 5, then we said there was one subset with cardinality 0. That's always the empty set. There are 5 subsets with cardinality 5, 10 with cardinality 2, right? So, yeah, this is basically telling us the number of subsets of each size. All right, so remember the size goes 0, 1, 2, 3, 4, 5. All right, so it turns out that those are the same exact numbers, which leads us to the more general idea of binomial coefficients. So here's our definition. For each integer n greater than or equal to 0 and integer k such that k is a number between 0 and n, it could be equal to 0 and it could be equal to n, there is a number that we express this, like this, and we read it n choose k. So it's kind of parentheses, and then we write the n on top and the k on the bottom, and it's n choose k, where 3 different things are true. So n choose k is the number of subsets of a set of size n, each with cardinality k. So that goes a little bit to what we talked about in the last section. N choose k is the coefficient of x to the power k, y to the power n minus k in the expansion of x plus y to the n. So in our example, our n was equal to 5. So I'm talking about this example that we just did right here. Our n was equal to 5 because that's right here, the exponent of x plus y. And then, for instance, when k is equal to 2, then we're talking about how many x squared terms there are, and that is exactly this right here. And the coefficient there, as we can see, is 10. Okay, so that's kind of what that bullet point means. And then the third bullet point, n choose k, is the number of ways to select k objects from a total of n objects. And that kind of relates back to the first bullet point, talking about the number of subsets. And we're also going to talk about n choose k as being the number of ways to select k objects from a total of n objects in the next section. Okay, so don't worry too much about that third bullet point there. All right, so moving on, we have these binomial coefficients now, And to organize them, we like to put them in something called Pascal's triangle. So what this is these are all the different values of n choose k, right? So here we are starting, the first row is when n is equal to 0, second row is n equals 1. So remember, it's always n choose k, so the top number is n. This is n equals 2, n equals 3, and n equals 4. Of course, n could be any number. This is just kind of a snapshot of the top of the triangle. And then in each of these rows, the value of k increases as we go from left to right. So it starts at k equals 0 and ends at k equals n. All right, so the first one, the only choice when n is equal to 0 is k equals 0. That's a little bit boring. But the second row, when n equals 1, you could have two different values of k, which are 0 and 1. When n equals 2, k could be 0, 1, or 2. So again, you just see that the value of k is increasing as we go from left to right. All right, so each of these n choose k's is, we can evaluate that to an actual number. Oops. And what that looks like is this down here. So this is a picture taken from your book. I forget what page it's on, but you can find it in your textbook and also right here. So again, this is starting the row with n equals 0, n equals 1, n equals 2, etc. And then the k increases as we go from left to right. So for instance, when n equals 3, then this corresponds to k equals 0, k equals 1, k equals 2, k equals 3. So for an example, I guess if we wanted to know what is, I don't know, 8 choose 6, we could find that right here. So remember, this is our value of n, and this is our value of k. So to evaluate that, we have to count down to the 8th row, but remember we're starting at 0, so that's a little bit weird. So this is, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the row right here corresponding to n equals 8. That's also convenient that we can see kind of the n value is the second number in the row, which is convenient. But then we also need to find k equals 6. So remember, k starts with 0 as well. So here's k equals 0, 1, 2, 3, 4, 5, 6. So it turns out that 8 choose 6 is equal to 28 because we found the 8th row and then went over to find k equals 6. All right, so that's how we find the values in Pascal's triangle. All right, so then I do some more examples here, and I've given a video solution so you can watch that next before you attempt